Hello, everyone. Thank you for joining us, and welcome to today's Ask the Expert presentation, sponsored by Qualmark. I am Gail Eckert, Director of Marketing, and I'll be your moderator for today's. Tom Peters, Director of Qualmark's Center of Excellence. Welcome, Tom.
Thank you, Gail, and thank you, everyone, for joining us today. Last year, we put on a series of webinars centered around effective HALT testing, and that was been a very popular series, and we have provided the recorded webinars on our website. There's two places that you can go to review those recorded webinars. There's a special landing page on our website under www.qualmark.com, Webinars, Effectiveness Series, and you can also enter through the Qualmark website via Resource Library and look in the reference library, and you'll find the webinar link there also. This year, the Center of Excellence team has planned a special series on HASS. Today's presentations are first in that series, and Chris LaPlante and Neil Dortenbaugh will be the presenters today discussing the data used in HASS. So from here, we'll turn it over to Neil and Chris. Chris, would you like to lead off?
Thank you, Tom. Thank you for attending today. In order to implement a HASS program in production, the product must first go through HALT. Our discussion today will cover how the data from HALT is most effectively used in implementing a successful HASS program. We will review each type of data that is generated during HALT, which we summarize here on the summary page, and the importance of the data when moving into HASS. One data point we will cover that you do not typically discuss is the use of KPIs, or key performance indicators. We will show how they are generated during HALT and used in HASS. Before we get into the main discussion of the presentation, I'll turn it over to Neil for a brief summary on the fundamental concepts of HALT and HASS.
Thanks a lot. I find that it's a good idea to go through a few quick slides discussing the basics of HALT and HASS, just to be sure we're all on the same page. There are not rigorous definitions for the test processes, so this is what we're talking about when Qualmark describes it. First, we'll talk a bit about HALT. It is an iterative process applying stepwise increasing stresses to a product, thermal or vibration or combined stresses being applied, continuing to step the stresses up with the product being functionally tested the entire time until we find a failure. At that point, we're looking for hard failures or soft failures. Operating limit is a soft failure. You back the stress down and it recovers. The destruct limit is where we found a hard failure. Once we have something in our hands, a malfunction of some kind, then we'll move into a failure analysis phase. If you are doing this work in your lab, then you can stop for a while and do some failure analysis, or maybe you'll set it aside if you're doing work in an outside lab and do it later. But develop some workarounds perhaps, figure out a way to continue the testing, continue increasing stresses, make these improvements, and see if you have achieved maximum robustness. By that we mean you've hit the point where you are fixing everything that it makes sense to fix, and you have ruggedized the product as much as you can using that particular stress. Then you'll switch to a next stress, continue in that stepwise fashion until you've gone through all the stresses and achieved maximum robustness for your product. To maintain that for the life of the product, you want to move into a HASS program. So you take the data that you've taken from HALT and develop a HASS screen and a proof of screen, and finally progress into a HASS or audit screen. These are just a few basic, I kind of say, the mantras that we chant when we talk about HALT. One of the first things to keep in mind to understand it, the way we do it, it is not a test that you pass or fail. It's a tool for design engineers. The only way really to fail a HALT is to not find any failure modes, because that's the value, is to go away with failure modes in your hand. And there are no pre-established limits. You don't have a point where you stop. You keep going until you are finding failures that you can't do anything about. The product tells you the limits. So you are stressing to failure, and it is critical to be monitoring the product while you're testing. That's one of the fundamentals of HALT. You find failure modes that way that only show up under stress, but then go away when the stress is taken away. And those are the types of failure modes that show up as NDFs later when you get in the field. The primary output from HALT is margin improvement. And here's a slide. Some of you who are familiar with HALT have seen slides like this before. We have a stress indicated here. Must be a thermal stress because we're defining lower and upper limits that we found. These bars represent the limits of the product that was tested in HALT. So we have a operating limit and a destruct limit on the product or products that were tested in HALT, and a margin between the operational specs and the actual limits that we found, both an operating margin and a destruct margin. Even though the failure on the unit in HALT was outside of product spec, there's a distribution around that failure mode. We don't really know how big. It may be in your operating specs and be an out-of-box failure on 1 out of 1,000 units. The goal in HALT is to identify these failure modes and get rid of them so that these distributions can then be moved out. By maximizing the distributions, we maximize the life of the product in the field and minimize warranty costs. Now these products can age and these can creep in the field, and you will still have a product that's functioning well within its product specifications. And once you have implemented all of those improvements, you can move into HASS, the highly accelerated stress screen. Obviously, HALT is the design, is done in the design stage before the product is released. HASS is a production screen. The goal here is to detect and correct any changes that have occurred. Something changes in the design because of ECOs or a process change or a component change will be spotted. You can cut production time and cost because HASS will typically replace a burn-in and is much faster and finds more than burn-in can find. So you'll have increased out-of-box quality and field reliability and enjoy the added benefits of decreased field service and warranty costs. And in those first 6 months of product release, when you're finding design infant mortality issues, you will have chased most of those out in HALT or in the HASS screen, and so at product introduction, you're catching things in HASS and not letting them get out into the field. The limits that we use in HASS are based on what we learned in HALT, on the data we found in HALT. And the key pieces that we need to know are the operating and destruct limits found in HALT. In some cases, we'll have a two-stage screen, and that's what we describe here, a precipitation screen and a detection screen. The product will go through the precipitation screen first and then the detection screen. But the key is that these are based on the data that we get out of the HALT. The profile development is a key part of HASS. You base the initial profile on HALT information. We have some rules of thumb. We'll go over the 80-50 rule of thumb where we're starting our thermal limits at 80% of the span that we found for operational limits in HALT, and we'll start our vibration at 50% of what we found for destruct limits in HALT. Look at where we're going to be doing functional tests during that profile, and if there are product-specific stresses that you're including, like power cycling or loading of inputs and outputs or various other things you can do, decide where to put those within the profile as part of that HASS development. So that's really the 10-minute introduction to HALT and HASS, and that's what we're going to be talking about as we move through here. And you can see we have several different pieces of data that you can get out of your HALT testing. And what we're going to step into now is each one of those pieces of data and how they're used when you are developing your HASS screen. And the first we'll talk about are the operating and destruct limits that I mentioned just a moment ago. Now here is a graphical representation of a typical HASS profile, thermal and vibration, when you do a two-stage screen, as I described before, where we have first a precipitation screen, followed by a detection screen. The levels that we go to thermally during the precipitation screen are based on the destruct limits that we found in HALT. Those are indicated here in the red. We stay within those destruct limits. We do not expect to be doing damage to the product here. We're going to be shipping these. This is a production screen. But we are outside of the operating limits that we found in HALT. So the product will not be functioning, but we won't be taking excessive life out of it by getting too close to these destruct limits. So the power is off to the product during this portion in the precipitation screen. We're not functionally testing. After you've finished stressing at those levels, we switch to a detection screen, power on, and start testing the system. And we're reducing the stresses so that now we are within the operating limits that we found in HALT. You see here an indication for the vibration that we're having a more aggressive vibration level during the precipitation screen, then move to a cycling vibration in the detection screen. What actually happens for vibration during precipitation and detection will be based on what you know about the product and what you learned in HALT for the absolute limits and what is most effective for your testing. In any case, these levels are starting out at 50% of the destruct levels that we identified in HALT. Now, I've said this is the idealized, if you will, screen, this two-stage screen. The only time it works is when you have a significant delta between the operating limits and the destruct limits for your product. It's often the case, once you finish HALT and you've done things well, that the operating limit is very close to the destruct limit. Your unit will function and function well right up to the point where it finally falls apart, in which case you don't do a two-piece screen. You'll just do a detection screen. You're powered on continuously, monitoring continuously as you cycle within the operating limits and do your testing. And almost always, the production screen is a combined environment of vibration and thermal. We need those destruct limits and operating limits from HALT in order to develop the HASS screen. And that's the first key piece of data that we need to have. The next thing that we look at are the design limitations for the product and the process limitations for the development of the product. And those can be different in HALT than in HASS. And we'll discuss that a bit as we go in. When your product configuration, when you're in that final HASS environment, is often quite different from what you did in HALT. When you're doing HALT, you're focused on doing the most effective HALT you can. And that often means taking boards out of upper-level assemblies and fixturing them directly to the table and testing them as sub-assemblies. And you're not too worried about scratches because you know that you're going to be testing these boards to failure anyway. In HASS, you'll be testing often a full-up assembly, depending on where things fit in your production cycle and how things are most effective. So you can be getting very different response. Your functional testing can be different. And the limits that you test to can be different. If you finished your HALT without having plastic involved, and now in HASS you have your plastic case that you have to have in there, that's certainly going to affect what you use for limits on your screen. And your fixturing considerations change dramatically when you get into HALT because of the design limitations that you'll run into, particularly cosmetics and plastics. You have to worry about when you think about your fixturing. So you have to keep those pieces of data in mind as you move into HASS. Another key thing to look at, and especially when you know you're moving into HASS after you finish your HALT, is product response, to be monitoring exactly what is happening on the device that you're testing in the areas where failures are occurring. So, for example, if you have a full-up assembly in HASS that you're testing, you want to monitor and understand what's going on at the level that you did the HALT, at the product or subassembly that you did the HALT on. Here's an example to consider. If I have a product that in its upper level is a card cage with cards inserted into it that plug into a motherboard. Now this is a HALT fixture that you see here, but the product is in its system level HASS configuration. And you have done HALT on those boards in the most effective way you can think of, which is to do it securing the boards to the table like this. You get far more energy into the boards, and you're more likely to find the failure mode you want to find. How do I take what I learned in HALT at this level and use it to determine my stress levels when I finally get into this upper level HASS configuration? And let's take a look at the differences that we saw when we looked at vibration response on these two assemblies. As you would expect, when you put the card in that upper level assembly, you get much less vibration transmitted into it. This is a power spectral density graph showing the response on the circuit card and at the same set point levels. And what you see here is the spectrum on the card itself when it's being fixtured directly to the table. You see some nice low frequency excitation here that's the resonant characteristics of the board, and then the high frequencies coming through here much better than they do here, which is what we expect because the sheet metal assembly, like you saw for that card cage, will absorb a lot of that. And here, and as you can see when you look at that total GRMS number difference between the two, we're just not getting near as much excitation into those inner boards. Now, if I was setting up a screen and saying I want my vibration level in HASS to be half of the vibration level in HALT, I would not change my set point by half. I would look at these levels and say I want to reduce my product response by half. And actually, in this configuration, that's exactly what happens when I move the subassembly into the upper level assembly. So my set point, chamber set point for HASS, would very well wind up being the same as it was when I did HALT on the subassembly. So a careful consideration of the difference between the product response in the HALT environment and the product response in the HASS configuration is important as you move into HASS and decide what to look at to determine your screening levels. And one last point I want to bring up here is key performance indicators. I think most of you have heard the term before, I think, of KPIs. Basically prognostics or other information that you can gather from your product that will tell you not necessarily that it is failing, but that some indicator of performance is showing a degradation. Something is starting to slip. Hasn't gone to the point of failing yet, hasn't gone to the point of being out of spec yet, but it gives you a barometer that something is happening. When you are in HALT, you're actually driving the product to failure. So you have a chance to determine which factors that you think might be good indicators of impending failure are good indicators by monitoring them during HALT. When you find out which ones are the best ones to look at, you can use those in HASS to put more resolution and more efficiency in your functional testing. And here's an example of testing that was done and a key performance indicator that was identified on a device. Here the performance indicator was IOs per second. I don't know if you can read the legend there, but that is IOs per second. And here on this axis we have temperature. We had 3 units that were being tested, and you can see This one, in particular, showing significantly worse performance in IOs per second as temperature increases, versus, in particular, the green one, which held up very well. This purple line shows some degradation here, significant degradation here. At the end of HALT, we found that this device and this device were the first to show hard failures with temperature. So that told us that IOs per second, as temperature was increased, was a good indicator to look at to tell us that we might have a device that is failing. And that is something then to watch in HALT to see, in HASS, to see if there is a shift as production moves up. You see at the beginning, at ambient, they're all about the same. But as soon as we started increasing temperature, this guy started complaining right away, and this one later, we saw significant changes in. So that tells us, let's figure out a way, let's make sure that our functional testing is giving us this IO per second number, and we can make decisions based on that as well as our pass-fail criteria. So with that, I think I'm going to turn things over to Chris for a while and let him continue on through our data.
Thank you, Neil. If you recall, one of the goals of HALT is to force failures on the product. This is a valuable data point that should not be ignored. A successful HALT will provide various failure modes that should be addressed before getting into production and before you reach the HASS. By determining the root cause of these failures and performing corrective action, the product can be improved before reaching the production level at where you will not want to find those failures in production, which can cause delays in product release, and it'd be more expensive to fix at that point. If a failure is found in HASS that was not found in HALT, that'll could indicate a shift in the process. And
you can see from the Pareto there, the concept is that if you haven't actually done a full corrective action on something in HALT, it'll show up as the production failures in the field later, or in final test in-house. Hopefully you can catch it before it gets out. But in any case, you will see the failures in HASS or see them in the field if they haven't been corrected in HALT. That's an almost universal rule that those who have been burnt can attest to, that ignoring a failure mode in HALT simply because it was so far out of spec, it just about guarantees that that's a failure mode that you'll see in production. And if there are failure modes that you've chosen to ignore in HASS, or in HALT rather, keep those in mind as you look at what comes back from the field. And watch your Paretos in terms of what HASS testing did for you.
another data point to look at is the functional testing criteria, which will change between HALT and HASS. In HALT, often the functional test is custom and specialized in order to look at particular concerned areas of the product. And when you reach HASS, you will have more products to be looking at a time, and you'll want the test to be automated. And, go ahead.
You can see when you finally get into your final production testing, you can very well be testing many units at once, and your functional test has to take that into account. In HALT, we have the luxury of testing just a few products at a time. And also, when you're doing the HALT testing, you'll have a lot of points installed hoping to catch some key performance indicators that might be valuable. Once you've found those key performance indicators, you can reduce the amount of test fixturing that you need in HASS because you know which ones you're really looking at. So those are the key things to be considering as you move into functional test in HASS. I've got to be doing more units, and what do I really need to do for functional test to catch the failures I need to catch? What did HALT teach me about that functional testing? And then the last point, I want to talk a little bit about fixturing. The folks who are familiar with HALT know that in HALT, the fixturing can be fairly straightforward. It's you only have to build it once and make it work once, and you're not too worried about having everything uniform as long as you're monitoring the unit under test. You know how it's being stressed. So you wind up with some straightforward fixturing using 80-20 pieces and lots of aluminum U-channel and all-thread rod. And if it takes half a day to set up, that's just about right. When you move into HASS, you enter a completely different world from a fixturing standpoint. Now you have a host of considerations. Multiple units going into the chamber. Now the units can affect airflow, so uniform temperature across the units becomes a concern. And certainly uniform vibration across the units is important. And as you move from unit to unit across a table, or from insertion to insertion, as you pull units out and put new units in, you want them all to see the same vibration. And that becomes a key point in the design. Now you've got lots of cables to handle. Cable management becomes an issue. Cosmetics on the product are an issue. They can't stand. There's too many times I've come out of HALT and I've deaded the product putting 80-20 on it. You can't put up with that in HASS. It's got to be beautiful when you get done. So there are many considerations: speed of load and unload, human factors. You want to be sure that you don't leave any fingers in there with the units once everything gets packaged up. All of that has to be taken into account when you move into the high-volume HASS environment. The fixturing challenge is significant enough that many people will come to Qualmark for assistance in that. We have experts in designing HASS fixturing, and that's a service that we can provide to guarantee that no key pieces like that are overlooked. How you have fixtured your product in HALT is important to know when you make the move into HASS. It's not unusual to actually have a change in product orientation from HALT to HASS. If we were testing for here you see these are power supplies that are put into the unit. We've got them oriented so that we can get as many into the system as possible at once. When they were tested in HALT, they were tested rotated 90 degrees. So by monitoring the product itself, the board inside the device, we're able to determine the effect of that change on the stresses that were applied to the product and adjust the fixturing and the screen accordingly. And the one last big difference. When you are doing HALT, as we've discussed, it is not a pass-fail test. HASS absolutely is. You have to establish specific pass-fail criteria to say, when do I pull a unit out and when do I let it go? And this also reminds us that failing in HASS is really a more important thing than failing in other places in production. A failure in HASS is a red flag. It's an indication that something has shifted, something that has been stable in what you did HALT on and stable before has suddenly changed. And you need to very quickly understand, is this a one-of failure due to some a component that simply wasn't soldered down right, or have we got a shift in process or a shift in component characteristics that is affecting the entire population? Because HASS will show you the edges of distributions of shifts. So you have to jump on a HASS failure and pay attention to it. It's very dangerous to say, well, let's see if it shows up again, and then I'll do a real failure analysis on it if it pops up tomorrow. Because by tomorrow, you could have 10,000 units that have the problem. So there absolutely is a case where you either say go or no go when you implement HASS. Now, the KPIs can be a very sensitive indicator of process shifts for you. And it doesn't necessarily say, I've got units that are failing. It says, I've got a change I need to understand. So the KPIs are clues to point you in a direction to say, I need to understand what's happening and what's causing this. Let's make sure I haven't got something new introduced. Now, one of the things that we emphasize in HALT and is important in HASS as well is the whole concept of the value of failures. And too often, failed units are the ones that are thrown away or put in the bucket in the field return depot, and they're not paid attention to. It's important wherever you find a failure, if you're doing HALT on subassemblies or you're doing accelerated live testing, reliability growth testing, once you finally get the unit out into the field, it's actually failed in customer hands, all of those failures come back to be fed into your FRACAS system and the failure modes understood completely, and then update the FMEA that you did or the FMECA that you did so that that information can be retained and used for future designs, and the FMECA continues to represent the product as it exists now with improvements that are introduced as a result of those failure modes. But all through here, realize that whenever you have a unit that has failed, it's a piece of gold for improving your product and reducing warranty costs in the future if you bring it in, pay attention to it, correct it, and then remember what you did. So there's a lot of things that we've gone over here. If you'd like to get more information on any of this, contact Qualmark's Center of Excellence. The whole process of implementing HASS, taking that HALT data, and getting the screen up and running quickly and smoothly can be a daunting task, and that's something that our body of expertise that we have here at Qualmark can help you with. So we can provide you with more assistance. Email us questions. We're certainly going to be answering questions here shortly, and we will be responsive to you in any way we can. And certainly check out that resources tab at qualmark.com. There are a lot of papers there, a lot of presentations, a lot of webinars to be listened to that can provide a lot of knowledge for you. You can email us at excellence@qualmark.com. And that's the end of the presentation. Gail?
Yes, Neil, we do have several questions. I'm going to revisit slide number 15 here because I believe that's where the question came in. Mostly it has to do with set point. Does the set point of the temperature take into account the component operational spec?
In general, it's sort of irritating sometimes to design engineers as they begin to understand it, but the component spec is something that is largely ignored when we move into HALT and HASS. We use the data that we get from HALT to define what we're going to do in HASS. If a component has operated to a certain level beyond its specification in HALT, then we use that level, guard banded, as what we expect it to continue to operate in HASS. If something changes and that level drops, then it may still be within its own spec, but something changed. And we need to understand what. Because who knows where we're hitting in the distribution of its specification or of its tolerance to that temperature, and there may be 5 out of 1,000 that are outside of their specs. They're not performing up to specification at that point. So unless it's a hard limit that is something that we understand, and if we take it to that point, it's going to melt down or go black or whatever it is, we won't worry about what the actual specification is.
When fixturing, does the real-world mounting technique carry much weight?
If you've got, that implies that you're doing subassembly testing. So you have a fixture, you have a device that is mounted into something else, and you've got that device and you're trying to decide what to do for fixturing. As a general rule, no, unless it is very nice and convenient to use the mounting that is used in the end-use environment. One of the key things that we talk about in HALT that wasn't on the slide was stimulate, not simulate. We're trying to stimulate failures, not simulate an end-use environment. If I find that fixturing it in a different way will get more energy into it and make it more likely to show me good failures, then I'll fixture it that way. And that is, so in general, no, I don't worry about it too much.
Here's a double-barrel question.
Okay.
What does one do during hot and cold testing when testing electronic products that have components designed to shut down at high heat? Also, products that have batteries that cannot be removed, thus exposing them to heat, poses a safety concern. And go ahead and answer that, and then I'll ask the second part of the question.
Okay, and that's a very good one, actually. In HALT, of course, when we have known limits like that, we'll try to figure out a way to get around them, disable temperature limitation circuitry because we want to see the failures. And so we'll try to figure out a way to get around that. Thermal isolation, tricks like that. Tell me the second part of that question again, please.
Well, you know, you're concerned about batteries, the safety hazard.
Oh, the batteries, yes. Those are similarly, we'll universally remove batteries in a HALT environment because we know how they fail and it's nothing we're going to be able to do anything about. So we'll put them on extensions and take them outside. When you move into HASS, you have a whole other challenge because we will find if systems have thermal limits that cannot be overridden in software, and that often you can override a limit in software if it's something that the processor is watching and shutting you down. You can use custom test software that lets it go wider, and that's recommended in HASS. If you've got a power supply that's just going to shut down, you're not going to learn anything from seeing it, and that will wind up being the limit for the hot temperature that you can use in HASS. With batteries, if at all possible, I like to even do HASS with the batteries out and then insert the batteries later. If that's not possible, then you have to let the batteries limit the temperature because, as we all know, you can do all kinds of bad things by getting batteries too hot. And that can limit what you do in HASS.
And one other thing to take into account is part of the HASS implementation is to determine where in the production cycle it makes sense to do your testing. So there can be points at assembly that would provide you the advantages of workarounds over some of the thermal limiting factors in a product.
Yeah, at this point you'd look at subassembly testing and look at the trade-offs. Maybe I want to HASS at a lower level assembly and then build it up into the final assembly, look at that final assembly and say, what would I miss by shipping this without HASSing the upper level assembly? It might make sense to do it at that lower level assembly.
Okay, guys, we're getting pelted with questions.
Oh, good.
So, let's see if we can get through them here.
I'll answer fast.
Did we get the second half of that one done? Can you skip HASS and go right to a HASS? For example, if you work with high volume products, parts per million that are manufactured across various sites? What's your recommendation there?
Well, that's one of those. There's a lot of engineering judgment that goes on in implementing HALT and HASS. And when you're looking at millions, you decide, I can't do HASS, I've got to do a HASSA. In a case like that, as you implement the HASSA, I guess answer number one is yes, you have no choice. We've got to go straight to an audit. But I'm going to do the highest percentage of units I possibly can at the beginning, limited by my budget for equipment, and get as much through the chamber as I can to collect data on failure modes and failure rates so that I'll get the confidence level I need about the functioning of the test, and I'm going to be really jumping on any failures I find, because you could very well be honing in on some last design issues that might have slipped through HALT. And if you have some other 100% test that you're doing, keep it going for a while until your confidence in your HASSA is high enough that you can cut it off.
Okay. And so let's just kind of clarify, because there is the question, a couple of them out there. Does one conduct HASS at 100% with production units? So kind of explain when to do HASS and then when you move to HASSA.
Right. By definition, the last S in HASS is a screen, which defines 100% of the product going through it. So HASS is always considered to be 100%. When you want to drop to an audit, HASSA, the highly accelerated stress audit, is what you're talking about, and at that point, you're picking a percentage and doing just a portion of the product that you're testing. You can indeed make the move from HASS to HASSA, and you can do that based on failure rates, in the field. There's guides for that. Actually, IPC's standard for power supplies has a nice definition of failure levels to look for as you make the decision to move from HASS to HASSA, and then to reduce the number of units that you run through a screen in HASSA. And it's all based on failure quantities in the field and failure quantities in final test, failure quantities in the screen.
And how long should the HASS profile last?
You know, that's often determined in the proof of screen process for the HASS. In general, as a rule of thumb, again, I like to look at 5 thermal cycles, mainly because, and even if we have to reduce the stress levels some in order to get 5 cycles without causing undue stress, which is what we would find out in proof of screen as we ran it through that many, many times, then in time, as I can watch where my failures are happening in that 5-cycle screen and shorten it if all my failures are happening in the first and second screen, or realize that I need to make it longer if I'm seeing things failing throughout the screen. So in general, 1/2 to 2 hours, depending on how long functional test takes, is what you can sort of budget for a screen. And you like to do 5 thermal cycles, and that'll be determined by how fast you can change temperature in the chamber. And I run about a 50% duty cycle on vibe at a 50% level for starters. But proof of screen tunes it all in.
And functional testing has a big effect on it.
Yeah, how long it takes to do the functional test is a critical piece.
Okay, so speaking of proof of screen, I've heard that for a proof of screen, to make sure that the HASS is not creating degradation or failures, you should take a unit under test and run it 20 times in HASS. Is that a good rule of thumb?
Yeah,
what do you guys suggest?
Yeah, a lot of years ago we used to say 10 times through the intended screen with known good units. If you don't see any end-of-life failures, then one pass through the screen is not going to take more than 10% of the life out. Well, we found out we wanted to be a little more confident than that, and also once you finish HALT and do it right, you can go through that HASS screen many, many times. without seeing a failure. So we say now 20 to 50 times through the screen with no failures that are end-of-life type failures. Then you've got a screen that you can go through a couple of times if you need to in production. If you have a failure, you fix it, you run it through it again, without taking more than a 20th of the life out of the product.
How do you determine the ramp rate during HASS?
As a general rule,
this particular person is talking about mechanical gears.
Okay. As a general rule, I don't hit on it a whole lot because we don't step up ramp rates in HALT. We go at maximum ramp rate and see what happens, because it's not that often to find a product that can only tolerate a certain ramp rate. And if you ramp it faster, then it begins to wear too much or start having destruction because of the fast ramp rate. So in general, we're ramping as fast as the chamber will allow in all of this testing. If we have a specification for it, it's 60 degrees C per minute. So we run those ramps as fast as we can. If we find out that there is some reason why that can't be done and something we're doing damage, and we would find that out in proof of screen, then we back the ramps off and control them to a slower rate. But typically, you're going as fast as the chamber will go.
This person uses power supply as an example. Is it valid to test a component such as a power supply in HALT and then test that power supply in a final product, or must the test in HASS be conducted with the power supply on its own?
If you are testing sub-assemblies like a power supply, and then you build that supply into an upper level assembly and do HASS on that upper level assembly, the question is, should I HASS the power supply separately, or is HASSing the supply in the final product good enough? And I'd almost have to turn that back around and ask the customer, because it will depend on how isolated that power supply is in the final assembly. Am I going to be able to stress it enough to find failure modes that are valid, or is it so isolated once it gets in the final assembly that I'm not really doing an effective HASS on it? Are the limits for that power supply vastly greater than the limits for the rest of the assembly? If so, I may not get a highly stressful test on the power supply like I want to get. So I'd need to test them separately. If, however, I get good excitation into the power supply in that upper level assembly and its limits are similar to the limits of the rest of the assembly, you can do the HASS on the full up assembly. So it depends very much on the device.
PCB board has communication issues during ramp rate and not during dwell in a HALT. What does that imply?
Oh, you've got a good one on your hands there, because ramp rate is one of the things that ramp rates, past ramp changes does, is you'll have different rates of change at different points on the board because things are changing so fast. And you can have the ICs or the surface mount components changing temperature before the board underneath them changes temperature. And the changes, all of that is happening very dynamically. And if during all of those shifts something hiccups and sneezes, then you know that there's a tight timing issue somewhere that is only showing up while everything is changing. But once things stabilize a little bit, then you're okay. You could also have a thermal response in a component that, as it is in the process of changing, you know, maybe one capacitor is changing faster than another capacitor, and so for just a moment, timing is screwed up enough that the communication gets messed up, but once everything stabilizes, it's okay. So what that tells me is let's look closely at the timing that can be going wrong and causing the communication issues. Something's just slipping out. That's what rapid thermal is good for.
Okay. What about if a product has already been released to market and HALT HASS is being considered reactively?
That happens a lot, actually. Where somebody says, "Oh, my field failure rates are so high, I've got to get a better screen. HASS looks good." And then they say, "How do we do HASS?" And we say, "Well, you start with HALT." And because you do have to do a HALT to find those levels. It's often the case that the majority of the failure modes have been found and eliminated from the product. In the first 6 months to a year in the field, you find a whole lot of what you would have found in HALT. Just, it's too expensive then. So we'll have to do HALT to find the limits. It'll typically be a faster HALT because we're not finding a lot of failure modes. We're just finding out what those absolute limits are. And then we will, as quickly as possible, move into HASS, watching the failure modes closely. But it's certainly doable and is something that we help people with all the time.
Okay. Acceleration levels across the table vary quite a bit. It is always different from the control level. What do you suggest as far as monitored data?
You know, when you're, I'm sort of the opinion that you don't learn much looking at the table specifically unless the product you're testing is accelerometers, because what you're concerned with is the response of your product. And when the product is put onto the table, you're really integrating or summing together the vibration from all of the attachment points that it secures to. If there are differences between those points, it doesn't make much difference in what the product sees. The trick is, when you get into HASS, that you want to have universal excitation on all the product. So, as part of the design, the fixture validation, you will take fixtures and put them at all of the intended locations and see that you get similar vibration levels on the product at each one of those points. You're not looking at the fixture at that point, you're looking at the product to see what it is finally seeing. In general, if you're doing testing on one of our units that is the single table units with a 3 foot by 3 foot or 4 foot by 4 foot table, you will see very similar vibration characteristics in the quadrants. So if you center fixtures in the quadrants, you'll see very similar vibration excitation for a given set point. If you get into our larger system that you saw earlier for doing specifically the high volume production testing, those 6 tables that are in that unit all give similar response. And if there's variations across the table, they can wash out when you get the fixture in there, or you adjust the fixture to compensate for them.
My product is very expensive, and I don't have more than one unit I can do proof of screen on. Can I conduct proof of screen with just one unit?
Yeah, but you better do it 50 times because you need to be really sure. You don't know where that one unit hits in the distribution. And yeah, I've done HALT and have people say, "Oh, and by the way, I need to ship this one when you're done because these things are so expensive I can't even afford to use one up in HALT." And don't usually let them get away with that. But yeah, if you just have one unit to use in proof of screen, then by all means use it and run that screen. Actually, if you have the time, run the screen to failure until you actually see end-of-life, wear-out failures in the product. Now you've got a confidence level for what you can do in HASS that'll really, it's a really secure piece of data. It can take a long time, though.
Okay. Thanks, Neil, Chris, Tom. We have reached the top of the hour. I would like to thank everyone for joining us today. I'd like to remind you that this is only the first in a series of webinars the Center of Excellence has planned on HASS. So keep your eye out on the Spotlight section of our home page for the announcement about the next in this series. Right now, it's tentatively planned for later in the month in March. Don't forget about the bundled recordings on effective HALT. If you missed that series last year, it provides some very key information on getting the most effective HALT possible. It's available to you in our library. All of our other past recordings are available there as well. Okay, great. Thank you, guys. And again, thanks everyone for attending Qualmark's Ask the Experts presentation today.